Have you ever stopped to think about the invisible rules that are making all our complex electronics work? Well, today we're going to crack the code that powers everything from your stereo right up to your smartphone.
I mean, really think about it for a second. How does one simple knob on an old stereo just smoothly control the volume? Or how does a dimmer switch make a light go from dim to bright? It feels so simple, but behind that one little action is some seriously brilliant engineering.
And that's because so many of the circuits we use today are like these incredibly intricate puzzles. And those simple rules of electricity you might have learned back in school, well, it turns out they just aren't powerful enough to solve these kinds of puzzles.
All right, so let's dig into that. Let's look at exactly why those basic rules kind of fall apart when things start to get really complicated.
You probably remember the basics, right? You can add up resistors when they're all in a simple line. That's in series. And there's another formula for when they're stacked up in parallel. For simple circuits, that's all pretty straightforward.
But here's the thing. The circuits inside your phone or your computer, they are not simple lines. They're these complex webs with crisscrossing connections and even multiple power sources. You can't just boil them all down to one single resistance. Nope, you need a much better tool.
And that is where Gustav Robert Kirchhoff comes into the picture. Way back in the mid-1800s, he came up with two beautifully simple yet unbelievably powerful laws that let us analyze any electrical circuit. I don't care how complicated it is.
Now, before we get to the laws, we just need to get two quick definitions out of the way. First up, a junction. And it's exactly what it sounds like. It's any point in a circuit where a bunch of wires meet up and the current has to either split apart or come back together.
So, Kirchhoff's first law, the junction rule, is just beautifully simple. It just says that whatever amount of current flows into a junction has to be the exact same amount that flows out. Think of it like water pipes, you know? You can't have more water flowing into a T-junction than what's flowing out of it. And this whole idea is based on a fundamental law of physics, the conservation of electrical charge. You just can't create or destroy charge at a junction. What goes in must come out.
Okay, our second key term is a loop. Super simple. This is just any path you can trace through a circuit that starts and ends at the exact same point. It's a complete closed loop.
And this brings us to the second law, the loop rule. This one says that if you were to take a little walk around any closed loop in a circuit and you add up all the voltage gains you get from things like batteries and subtract all the voltage drops from things like resistors, you'll always end up right back where you started at zero. It's kind of like a roller coaster. No matter how many ups and downs you go through, you always end the ride at the exact same height you started. And this one is based on another bedrock principle of physics, the conservation of energy.
So, okay, we've got these two powerful laws, but what can we actually do with them? Well, it turns out you can use them to perform a kind of perfect balancing act, one that lets you measure the unknown with just incredible precision. So let's imagine you have some component, but you have no idea what its resistance is. How could these laws possibly help you figure that out with almost perfect accuracy?
Say hello to the Wheatstone Bridge. This really clever circuit, developed by Charles Wheatstone, is just a brilliant application of Kirchhoff's laws. It's basically four resistors set up in a kind of diamond shape, and it creates these two parallel branches that you can balance against each other. So here's the key idea. You put your unknown resistor in one of those four spots. Then you start adjusting the other resistors, which you do know the values of, until a little detector in the middle, called a galvanometer, reads 0. When that happens, the bridge is perfectly balanced. It means there's literally zero current flowing through that middle path.
And here's the magic. When that bridge is perfectly balanced, Kirchhoff's laws all simplify down to this one beautiful, elegant equation. The ratio of the resistors on the left side is exactly equal to the ratio on the right side. So if you know three of them, you can find that fourth unknown one with just some simple math. It's an unbelievably precise way to measure resistance.
But we're not done yet. The applications don't stop there. What if we wanted to measure voltage instead of resistance? And what if we wanted to do it perfectly?
You see, a normal voltmeter has a little problem. To measure voltage, it actually has to pull a tiny bit of current out of the circuit. But in doing that, it actually changes the very voltage it's trying to measure. It's not ideal, right? So is there any way to measure voltage without disturbing the circuit at all? Well, yes, there is. It's called a potentiometer. This amazing device uses a variable resistor to perfectly oppose the voltage you're trying to measure. You adjust it until the current hits zero, finding that point of perfect balance, just like the Wheatstone Bridge.
And at that exact moment, it can measure the voltage without drawing any current from the circuit. It is, for all intents and purposes, an ideal voltmeter.
Okay, let's bring all this home now, because these concepts from the 1800s, they aren't just for physics labs. Turns out they're hiding in plain sight all around us every single day.
Kirchhoff's laws, the Wheatstone bridge, the potentiometer, these are the invisible engines that are powering so much of our modern world. They are the fundamental grammar of how we design circuits.
That volume knob on your stereo? That's a potentiometer. The digital scale in your bathroom? It's using a Wheatstone bridge with something called a strain gauge to precisely measure the tiny changes in resistance that your weight causes. Motion sensors, super accurate thermostats, the list just goes on and on. So, think about that. Two simple rules, figured out over 150 years ago, give us the foundation for controlling our entire electrical world with incredible precision. They are hidden absolutely everywhere. And that just leaves us with one final thought. What are we going to build with them next?